Trifon Trifonov at MPIA will discuss his Exo-Striker toolbox. Take it away, Trifon.
Thank you very much. So I hope you see my presentation. It's a PDF, so that's why I'm a bit worried. Do you see me? Okay. Do you see the full player here? Okay. First, thank you very much. I would like to especially thank to the EMAC team for their great job. Please keep going that way. I think the EMAC project is of great value for the community. So today I will be very happy to show you a few insights about the Exo-Striker toolbox. This is a project that I built in my free time, mostly for fun, but I feel that it might have a pretty good usage by the community, and it can be used by broad spectrum of people. For example, it can be used by fresh undergraduate students, their mentors, but you can also do some serious scientific work, and I hope to convince you in that. So what is the Exo-Striker? Basically, this is an open source, fast and versatile GUI toolbox for exoplanet orbital analysis and body simulations. I would like to mention that it's really inspired by the systemic project. I hope at least the more senior people here probably remember Systemic. That was a project developed by the Greg Laughing's team many PhD timescales ago. So I did my PhD with the Systemic tool. It was a really fantastic tool, a GUI-based tool, mostly focused on radio velocities and body simulations, which you can inspect many radio velocity datasets, find their orbital parameters, and etc. But over time, Systemic was kind of abandoned, unfortunately. It was not maintained in the last 10 years, I believe, and it lacks some modern tools like fast MCMC or dynamical nested sampling, for example, or it's not really Pythonic. So my agenda here was to build a Python-based, versatile alternative of Systemic, which can be used also for transit search, TTVs, and etc. So this is how it looks basically. I hope you see my cursor of the mouse. So this is the GUI started freshly. So this is a plain. This is the plain GUI, and I would like to mention for what it is made of. So as of today, this is the version 0.81. So you keep in mind that this project is probably never going to be finished. It's an ongoing work. So I have an idea to publish a paper when the version it's about 1, but this is going already a couple of years already. So it's never-ending work. But as of this version, you should know that this is more or less a Python tool, which beneath the Python frame, it has a Fortran code, which is doing the heavy lifting part, for example, calculating the dynamical models, doing the light curve analysis, and etc. And the GUI is based on PyQt5. And you should know that the whole GUI is quite modular, while just like Systemic, the Exo-Striker was meant for radio velocity, so therefore the models inside the Exo-Striker are internal to the Exo-Striker, but it stitches some well-known packages like Batman, TTV-Fast, and Celerite for additional modeling like transit, TTVs, and GPs. And recently, we also included astrometry together with Tom Shivy at the Landesteinwarte, and we can do all kind of combination of exoplanet data analysis with the Exo-Striker. And keep in mind, we can also do some best fit optimization, which was intrinsic to the Systemic. Also, sorry, I got a message. I'm not sure what this is about. So you can do also MCMC optimization and posterior distribution analysis, and also you can do nested sampling with Dynasty. We can do also some radio velocity in transit search and many other details which you can check on the GitHub page. Keep in mind that the biggest advantage of the Exo-Striker that it has a huge free of charge radio velocity database, which consists of over 300,000 unique radio velocities. Some of these radio velocities have been published in Paul Butler's paper in 2017 and slightly modified by Leftar-O et al. In 2019. And I also published the HARP Survey Bank in 2020. So you can take advantage of all these radio velocities with the Exo-Striker. So just very briefly, this is the GUI layout. So you have like 5 sections. You have a section for interactive plotting. So all your plots are happening here. You have a section for the help widgets. For example, you have a standard input-output monitor. You have interactive shells, more plots, and you have a couple of other important widgets here which can help you to write your paper, for example. You have a data parameter section where you can upload your data and retrieve some parameters such as the radio velocity offset and the radio velocity jitter, for example. And you have input and output parameter section where you can retrieve your orbital parameters and their errors. And finally, you have a section here which is basically statistics and control. Keep in mind that the Exo-Striker can be used without the GUI. So behind every button you see over here, there is a function that can be used interactively in the terminal. For example, you can power your Jupyter or IPython. You can import the Exo-Striker, create the Exo-Striker class object, add data, add some planets, and then you just fitting, and then you can do, let's say, run MCMC. So this is a very minimalistic example. It could be more complicated than that, but even this few lines of code can give you pretty good results. So just for you today, I prepare a brief demo of the Exo-Striker. So we will analyze a well-known 2-to-1 mean-motion resonance pair discovered on multi-telescope precision Doppler data, and we'll try to do it under 5 minutes. So this is the tool over here, plane tool. So generally, we can add the data here by clicking in the data buttons, and we can browse where your velocities are. But today we will just use the data inspector. So if you click over here, you get access to the free radio velocities that I mentioned. So if let's do 8 to 9. So I hope you can follow me. I'm not doing it too fast. I'm sorry. So this is the well-known two-planet system. It consists of 2 Jovian mass pairs in 2-to-1 mean-motion resonance. It's a fairly well-known system, HD 82943. So we have HARP's data for this system and also HIRES. But because of lack of time, I will just use the HIRES data today. And in the Exo-Striker, you can get the radio velocity, but you can also get their activity indices if you want to study, for example, bisectors and H-half analysis and etc. So let's use the HIRES data for now, and we can just load it to the Exo-Striker. So okay, here our data, and usually what people do, we expect to have a GLS periodogram, for example, and I know very well that this is planet 1, this is planet 2, but if you don't know, you can do some kind of a pre-whitening sequence. You can fit planet 1, refit, then inspect the residuals, then this one will pop up, then you can find the 2 planets. But since we don't have time and we're lazy, I have included a convenient button over here. It's called RV AutoFit. So if you click over here, in a few seconds, you have everything you need done for you. Okay, so you see the Exo-Striker already found you the 2 planets, and this is planet 1, this is planet 2. Well, we can do also, so basically we have the best fit parameters immediately, and we get some covariance matrix errors. Okay, so immediately we get the orbital parameters. We can go further. We can also modify the jitter, actually optimize the jitter. So we can use the simplex method over here. And now we get even better fit. And of course, if you want to study the parameter distribution, one can go to, let's say, to the MCMC or the nested sampling algorithms. They're basically using the dynasty and the EMC. Because we don't have a lot of time, I'll just do something pretty unreasonable. I'll just run an MCMC with only 200 samples just to save time. But of course, you generally should use more samples than that. So if you just run the MCMC button over here, okay, it says that it will take some time. And here we can get the progress. So it's first doing the burning phase, and now it's doing the MCMC phase now. And meanwhile, we can study the stability of this system. So if you remember, I said it's a 2-to-1 mean motion resonance system. So we don't know whether these parameters are actually stable. So we can go to the n-body section. So the Exo-Striker allows 3 integrators, the classical MVS plus general relativity per session, and the Simba algorithm. I'll just use the Simba, whatever we have over here, and just run. So very soon we should get Simba done. Okay, so we see the system is stable at least for 10,000 years. And you can study, let's say, the distribution of, I mean, the evolution of the semi-major axis and eccentricities. And you can check, for example, the evolution of the period ratio. So clearly, this is a system that is locked in a 2-to-1 resonance. So the mean period ratio is about 2. And if you go to the resonance angles, you can inspect θ1 or θ2. In this case, you can change the cover, for example, to export the plots for your paper. You can do also trajectory plots. So the people who know planetary dynamics well know that this system is deeply locked in a resonance. So while the MCMC is still burning, I just want to mention that the plots are extremely fast and extremely flexible. You can actually export these plots for your paper very easily. You can do matplotlib window, for example, or you can do it as a PNG, CSV, or whatever you like. What else you might want to know? So there's a large number of things you can export. For example, you can export all these parameters as a LaTeX table, so which can be ready for your paper. So this is a function that gives you the. So if you just open notes over here, there's an editor, and you can import it. So this is basically copy paste for your paper, and it's done. Okay, so the MCMC is done. One can check the parameter distribution with the Exo-Striker tool, or you can just go to the plot option, corner plot, and then you can just play a little bit with the samples. For example, I want pink samples with truth covers of, let's say, blue or whatever that is, and you just do make corner plot, and very soon we will have the corner plot done for us. And basically that is what I want to show. Just let's finish the corner plot in a sec. And yeah, it takes a little more time. I think WebEx is torturing my computer quite a lot. Okay. So what you can do is just open the bash shell and do ocular corner plot, and you get your corner plot, right? So if you want to publish a paper in Exoplanet Science, you need to have a corner plot. Otherwise, your paper might be rejected by the editor. So Exo-Striker can give you corner plots very easily. Okay, so I'll just go back again to the presentation. This was a very quick demo of what you can do with the Exo-Striker, and we basically were able to get corner plot, statistics, posterior distribution, LaTeX tables, everything you need for your paper, yeah, within 5 minutes. But you can do also some transit search. So basically, this is an example of WAP6 planet system. So this is the test light curve, and you can inspect it. You can find, you can do a period search with the transit least square algorithm, and easily you can get the period and its harmonics. So obviously, this is where WASP6 is resides in the orbital space. You can do also global data analysis. For example, this is the a well-known exoplanet system that was modeled by our Carmenes team with transit and radio velocity data. And you can do some GP modeling, for example. I probably won't have the time to go in details, but you see that, for example, this is the residues of the radio velocities, and this signal is not a planet. It's actually the star being variable, and this signal persists on the radio velocities and the light curve. And this is basically my final slide. What is next? There is need for more work, and this is a good time for people to join the project if they're interested, because we are at the final, but still there are many things that needs to be improved. For example, I would like to have improved the photodynamical model, which I'm not so happy with at the moment. We're working with including astrometry in the modeling to be ready for the Gaia data, and we are working on the Read the Docs webpage. So please stay tuned, and that's it for me. Thank you very much.
Thank you, Trifon. Let's give a hand to Trifon.
So did I think I did it for 15 minutes or so. Okay.
Yep, exactly. So we don't have time for questions right now, but of course, in the Discuss channel, feel free to ask a question and tag Trifon.